consider the Fourier transform of conjugate functions. Okay, complex conjugate functions. Firstly, the inside of the bracket is xj omega. Fourier transform of xt. Okay, we take the conjugate of them, so it means that the conjugate of xj omega, and this conjugate applied both of the xt and e to the minus j omega t, then it becomes the x conjugate t times e to the j omega t. This is equals to that one. Then if we taking the Fourier transform of x conjugate t are this one, x conjugate t, take the Fourier transform, we have to multiply this basis function minus j omega t dt. So compare these two functions. Just replace omega with a minus omega. So this one is x conjugate j minus omega. Okay, minus omega. X conjugate minus j omega. Okay, this one is Fourier transform of x conjugate t. You can compare, this one is that one. Then we replace the e to the j omega t with the minus j omega t, then it becomes the omega sign is opposite case. So conjugate function can be taken by these Fourier transforms, taking the conjugate and reverse the frequency. That is the time domain complex conjugate. Now consider for a real number. In case of real valued signal, conjugate is the same as the original signal. So if this is satisfied in a real number, then complex conjugate, Fourier transform of complex conjugate is the same as this one. I mean that the Fourier transform of xt is xj omega equals to this one. Then you can easily find out. This should be satisfied. If x conjugate j omega equals to minus x minus j omega, it means that the magnitude is even function. You know what, that the conjugate has the same magnitude, but the angle in case of conjugate is negative sign. So magnitude is the same for the positive and negative frequency, but the angle is opposite. So it means the angle is odd function. Xt signal is a real number, then in the spectral domain, this should be satisfied. So let's express that xj omega in the only positive frequency, then it can be expressed by magnitude. This is function of omega, and e to the minus j theta. Theta is also function of omega. So magnitude is function of omega, angle also function of omega. This one is xj omega. In case of real number, the negative side is complex conjugate of a positive side. Okay, positive side shows this one. Then negative frequency, it means the reversal frequency, magnitude is the same. It's a function of omega, but the angle should be taking the conjugate of them. You know what, omega is positive, it looks like this one. In case of negative, it should be taking the conjugate. So taking the conjugate is e to the j theta. Theta is a function of omega. So compare the positive frequency versus negative frequency. Magnitude is the same. That's this one. Magnitude is the same positive and negative frequency. So magnitude should be even function. What about phase? Phase is opposite polarity. So in this case it's minus theta, but this one is plus theta. So phase is odd function. Keep in mind, if a real number is a real number has the even function of magnitude of Fourier transform, but the Fourier transform phase is odd. In case of real number, this real number the signal. What about the real number, the even and odd function? We define the even function in this way: xt plus x minus t over 2. This one is even part of the xt. So the definition is this one: positive and negative side has the same value. In case of odd component of the xt can be written in this way. So by adding this even and odd component will give the original signal xt. So xt is a sum of even and odd function. It means that the original xt signal can be decomposed the even component plus odd component. xj omega is a Fourier transform of xt. Then by use of superposition theory, Fourier transform of even component and plus Fourier transform of odd component, we can find out the j omega by this the even and odd component. So now consider the even component Fourier transform of that. Then we can refer to this value. Due to the superposition theory, we can using that one, xt has xj omega, but x minus t is x minus j omega t because of the reversed signal. So it is this way. But we know that the xj omega is, you know, the x minus j omega, okay, here x minus j omega is xj omega conjugate. So xj omega plus xj omega conjugate sum. So sum of two different complex number, two different complex conjugate. Okay, xj omega plus xj omega conjugate will give the real number of them. So 1.5 is cancelled out by 2 of real number. What about in the odd function? In the odd component can be take the Fourier transform in this way. 1.5 is come from these two, and xt is xj omega, x minus t is x minus j omega, and take the subtract. But the subtraction of its complex conjugate will give 2 times j and imaginary part. 2 is cancelled out by this one, and j remained here, and imaginary part exists here. So in case of even real number, it has the real Fourier transform. So Fourier transform of Fourier transform of even function is real and even. So that is this one. So real number and even. One of the examples is cosine omega t. This one is even function. Then Fourier transform is a delta function. Okay, you can write down. Okay, delta omega minus omega 0 over 2 plus 1.5 delta omega minus plus omega 0. So this one is even function and the real number. And what about the odd function? Odd function is purely imaginary and the odd function. The example is a sine omega t. The Fourier transform of sine omega t is 2j over delta omega minus omega 0 minus delta omega plus omega 0. Now you may have some idea for the Fourier transform of complex conjugate, and also even function will have a real number, the Fourier transform, and even the Fourier transform itself is also even and real. Odd function have odd function of Fourier transform and the purely imaginary. Okay, this one shows that the purely imaginary, but this one is a real number. Next topic is convolutional property. Let's consider system. When we applied impulse to the system, then the output becomes the impulse response. Because of this property, sometimes usually we express that one with ht as a system. System can be expressed by the impulse response of them. So this one is that one. So when we applied xt, then our yt are given as a convolution of ht and xt. Convolution can be expressed in this way, and the same way is minus infinity to infinity, and the x tau times h t minus tau d tau. So it's the same things. So convolutional operation given like this way. What if the system is the causal? In that case, the impulse response exists only this one is positive, t minus tau are positive, then response exists. If this is negative, then there is no response existed here. So to satisfy this condition, tau should be less than by t to be non-zero response. So this infinity can be replaced by the t in case of causal system. So causal system can take in the integration range up to minus infinity to t. So it says that we only concerned in this period of time. T is the maximum time that affecting to the output in case of causal. If it is non-causal, we need to take in infinity at here. What if that input is a complex exponential function? Xt is a complex exponential like that. Then yt is given by this convolutional operation. Then it can be expressed in this way. H tau times xt minus tau are given in this way. At here, take out this j omega t part, then this becomes e to the j omega t times integral minus infinity to infinity h tau e to the minus j omega tau d tau. Okay, I have to erase this part. Okay, d tau. So look at here. This one is definition of Fourier transform of h tau. So it is hj omega. This part is a Fourier transform over ht. So we can express the output yt as a product of input and hj omega. So this is it. You know what, this one is a complex exponential input. If input is complex exponential signal, then the convolution is very easy. If we express the impulse response as hj omega by taking the Fourier transform, so hj omega product input signal is the directly output. Okay, so hj omega times etj omega. So this operation is not convolution anymore. This operator convolution is actual integrations. But if we already have the Fourier transform expression for the h tau, then we just the product of the input and output will give the output. So we do not need convolution operation at here. Just a product is enough to find out the output. So this one is make it simple for the system response estimations. For any input xt, so we just we do not assume the complex exponential anymore. For any given input xt is here, then the output is given by this convolution. So convolution operation shown here. We would like to find the Fourier transform of yt. Okay, then we have to take the Fourier transform for this convolutional signal. Then that is this one. So this part is this one. This one is actually output yt. Yt is take the Fourier transform. Then take integration both tau and t. Let's integrate t first, okay? Then x tau is here, and d tau over here, and ht minus tau is here, and dt is here. So t changing from minus infinity to infinity, ht minus tau times e to the minus j omega t. This part should be calculated first. Then let's try to find out this one. By changing of variable of this one, so let this one is x. So x is t minus tau. Then dxi equals to dt. And integration range, if t changing from minus infinity to infinity, x also changing the same way, minus infinity to infinity. So minus infinity to infinity, hx. Then t is x plus tau, so that is replaced here. Then e to the minus j omega t. T is x plus tau, so we can write down here x plus tau. Tau can be extracted out because it's not a function of x, okay, dx. So look at here, this one is Fourier transform of h, so this is hj omega, okay. So the tau is not function of x, so we can take out of the integration operator. Then it gives us the Fourier transform of hj omega. So this one is hj omega times e to the minus j omega tau. That's this part. Then hj omega is not a function of tau, so we just the integration over here, minus infinity to infinity. Then this one, this integration gives xj omega, and this one is hj omega. So in the time domain convolution, by taking the Fourier transform expression in the Fourier domain, it's just a product. So time domain convolution is a complex to make integration, but in the spectral domain, it's just the directed product. It's very easy to find out. So it is valid in any input. Yt is convolution of impulse response and input. Then in the Fourier domain, output spectral output Fourier transform equals to h transform hj omega, and input Fourier transform the product. So convolution in time domain corresponding to the product at the frequency domain. So this is the important property of convolutions. And here, what about the opposite case? In the previous topics, we talk about the convolution signal is take the Fourier transform, then it becomes the product. But in the time domain, product is taken the Fourier transform. What will happen? x1 and x2 is a product in the time domain. We would like to take a Fourier transform. This should be minus infinity to infinity. So this is taken Fourier transform. Then watch the x1 expression, x1t, okay, this expression. x1t is time domain function. So if there is a Fourier transform expression exist, then we can take an inverse Fourier transform of them. Okay, so 1 over 2 pi, taking integration minus infinity to infinity, x1 j omega e to the j omega t d omega. Yeah, this one is inverse Fourier transform of x1t. So we can replace this inverse Fourier transform expression for x1t, then it becomes this one. So this one should be minus infinity to the infinity, and this one is also minus infinity to infinity. And for the ambiguity, I just replaced omega with a large capital omega, like this one, and omega is a large capital omega, like that way. Then it becomes this one. and this part remained at here. So to avoid the ambiguity between this integral variable with this omega, so I take this large capital one, and then we need to consider this one is minus infinity to the infinity, or this one is minus infinity to infinity. Consider that one. Then we would like to take integration this dt first, then this one, and this one has a function of time. So by producting this one, that will give this factor, and x2t is this one, and the d omega are this one. Then inside of here, consider these integrations. In this integration, we can write down minus infinity to infinity x2t. This is a time domain function, and times e to the minus j omega minus large capital omega t dt. Then this becomes x to j omega minus large capital omega. Frequency shifting, okay? So it becomes this one, and x1 j omega this one. This should be minus infinity to the infinity integration. 1 of 2 pi come from this factor. So look at here, the x1 and x2 is integrated over omega. It's a convolutional operation. So it's a 1 over 2 pi times x1 j omega and x2 j omega are convoluted here. It means that if signal is a product in time domain, in the frequency domain is convoluted. So convolution operation is should be understood in the transform domain. Firstly, time domain convolution corresponding to spectral domain product. Time domain product corresponding to frequency domain convolution. Okay, I already talked about the time domain product and time domain convolution. Let's look at what's the meaning of that one. When we study the one time domain product corresponding to in spectral domain 1 over 2 pi times convolution. In time domain convolution becomes the frequency domain product. So we call that one is a modulation, the other one is a pulse shaping. Let's consider one of the example here. Here is a sending signal. We have some message to send st. As the spectral content is sj omega. It's shown here sj omega. Fourier transform of st looks like this one. It occupied bandwidth up to minus omega to the omega 1 to the omega 1. So this is bandwidth of the signal, and we would like to modulate with a carrier signal of cosine omega t. Cosine omega t has a spectral domain. It has a Fourier transform shows that the pi delta and plus pi delta. So it has impulse response minus omega 0 and plus omega 0. So to make a modulation, it means that the information can be loaded to the carrier. So that is done by this product. By taking the product, we make a signals RT. Then taking the Fourier transform, then the Rj omega Fourier transform of this one can be expressed by the convolution of P and S. Okay, the convolution of these two things. Okay, Sj omega and Pj omega take a convolution. The convolution operation shown here, it's just starting minus infinity to the infinity. And convolution can be done by these integrations. S omega and P omega minus omega. We take the integration omega minus infinity to infinity. Also this minus infinity to infinity integration. Then P omega minus omega are given in this expression. We just replace omega with omega minus omega. Then it gives in this way. So 1 over 2 pi and the pi gives 1.5, and the two different deltas. Delta omega minus omega 0. That's this part. And omega minus omega plus omega is this part. And take the integration over large capital omega. Then by the property of the delta function, omega is the integration rate variable should be equals to omega minus omega 0 to be non-zero. So this omega replaced by omega minus omega 0. That's this part. And what about here? Omega should be omega plus omega 0. So it gives like this one. Except that all values are 0. So it gives this result. Now let's interpret what's the meaning of this one. So you can see just the frequency shifting to the positive omega 0 taking scaled 1.5. So this one is moving to the omega 0, positive omega 0, and take the scale 1.5 of this one. So this is 1.5 times S J omega minus omega 0. Okay, this is this pulse shapes. The upper bound is omega 0 plus omega 1. Low bound frequency is omega minus omega 1. So this one is this part signal. The other part is a mapped to the negative frequency. It's moved to the minus omega 0. And similarly scaled by 1.5 and shifted minus omega 0. So this property is called modulation scheme. When we taking the AM modulation, we can move in positive frequency and the other one is a negative frequency. Because of this cosine omega 0 t are considered e to the j omega t plus e to the minus e to the j omega t divided by 2. So by this product, frequency shifting occurred for positive frequency and a negative frequency like that. This property is called modulation. What about the second one, pulse shapings? When we designing a filtering, we are using these techniques. Here is for filtering, we are using this technique. Data signal is ST, and pulse shape to filter is PT, and the output is expressed by the convolution of data to the pulse shape. By taking the convolution, what's going to happen? Take the Fourier transform, then we can see to make it easier. So in the frequency domain, it's just a product of these two signals. Here shows that the ST signal is in the time domain. And the pulse shape PT is given like that. And let us assume that the Fourier transform of a PT has some band limited signal like this one. So this one is a spectral domain, Fourier transform of PT. Okay. Yeah, Fourier transform of PT is PJ omega. It's a limited bandwidth is plus minus omega 0. So this one has this kind of functions in the frequency domain. Then by taking the convolution operation shown here that each pulse shapes are convoluted each impulse data like that. So after convoluting, the RT signal looks like this one. Okay, like that one. So this is the result of the convolution. The Fourier transform of this convolution is a product of this one and ST. You know that SJ omega will have a larger bandwidth due to this the impulsive signals, impulsive random signal is data. Usually digital data is impulsive random signal is quite wide bandwidth. But if you product in the spectral domain by this window, then we can effectively limit the occupied bandwidth of the RT signal. But if you look at here, PT actually is non-causal. The impulse response is applied here, then this part becomes the non-causal. Then we have some buffer allowed, then we can shifting that one into this way. Then pulse shape will be look like that one, and the Fourier transform is just the time shifting factor are multiplied to the PJ omega t, PJ omega. So this part is a time shifted version, but the magnitude response is the same. That's just the phase is shifted like that much because of this time delay. So by convoluting these two things, it looks like this one. This is ST data are shown here, and ST is convoluted by the delayed pulse shape. Then it looks like the same, like that. You basically this two things are almost the same thing except for the delay of the t0. So you can see here, by taking the Fourier transform, just only change the time delay factor of that. So this is the Pulse shaping techniques.